Now let's see the subroutine technique in action. The goal is to prove that the complement is undecidable. We have our recipe here one more time. So here, L prime in the recipe would be the complement, right? Then we're going to assume that the complement is decidable, and we're going to use the complement's Turing machine as a subroutine to arrive to a contradiction, and that contradiction would be us constructing a Turing machine for a language L that we know already that is undecidable, and therefore we have a Turing machine that decides L, and from this we arrive to a contradiction because this cannot be happening in the first place, right? So for this technique, the natural question to ask and the first question to ask at the same time would be, so what is the L that we will use? Remember, we had the halting problem, the diagonal language, bunch of other languages that we can use here. And how do we decide in between? So the answer is that we try to look for the easiest option. And the easiest option, 99% of the time, would be the most similar language to the language that we already have. So here, the answer is simple. Because we have D complement, most similar language to D complement is what? It's the language D, which is the diagonal language. So for L, we will use the language D, which is a diagonal language. And they are exactly the opposite. So our Turing machine will look more or less like we will use the Turing machine for the complement that we assumed as a subroutine. We will negate the result, and we will have the answer for the diagonal language. It's as simple as that for this first question. So let me make it more clear with an illustration. But before that, first, let's have our formal assumptions straight and clear. And this is how it should look in an exam situation. Anything less formal won't be accepted. So be careful here, and be careful with what you're assuming and when, like what you're implying, and exactly where you're using the definitions. So let me show what I mean by that. So we're assuming that L prime is decidable. So our L prime at the moment is the complement. So you say, okay, assume the complement is decidable, right? So this is our assumption. And now we need to apply the definition of decidability. What was the definition of the decidability? Here I paste it again. So a language L is called decidable if there exists a Turing machine M that halts on every input and accepts an input W if and only if W is in the language, right? So if we apply this to the complement, we have the following. So this assumption implies, by the definition of decidability, that there exists a Turing machine, let's call it M, that decides D, right? Here we transfer from the language itself to the existence of a Turing machine. And how does this Turing machine look like? We say, okay, M halts for all inputs, as in the definition. So maybe let's not call it inputs, but let's call it W, and accepts W if and only if W is in the language, right? Now that we have our assumptions straight, so we basically assume the existence of a Turing machine like this. So there exists an M, maybe let me duplicate, that takes W as an input. It either accepts or it rejects. There's no case that it doesn't halt. So, and this Turing machine M decides the complement. So that is the idea. We have this for our assumption, and from our assumption, we can use this as a subroutine while constructing the Turing machine for the diagonal language. All right. So how does this look like? It is fairly simple. So let's illustrate this and have the drawing for the Turing machine of MD, which is the Turing machine for the diagonal language. So again, we will use M as a subroutine. We will just negate the result that we have from M and we will output that. So let's say the Turing machine MD takes X as an input. We don't do anything with this input and we basically follow it to the Turing machine M. And as we said, Turing machine M either accepts or rejects. The only thing we have to do is to negate the result of the Turing machine M, because M decides the complement. The complement is the exact opposite of the diagonal language. So what we do inside the Turing machine of the diagonal language would be to negate the result, and then we would have the Turing machine for the diagonal language. So it's as simple as that. So I show this with another Turing machine. Let me call it I for inverting. And I do it like this. You don't have to do it. It is just for me to show it clearly. So after that, I say, okay, I negate the results and let me write it down first. And this means basically if M rejects, I will accept. And if M accepts, I would reject. This is the idea of a Turing machine for the diagonal language. If we have a Turing machine that decides the D complement as a subroutine. So this by itself is the contradiction. And why? Because we know for a fact that the diagonal language is undecidable. If we have a Turing machine that decides the diagonal language, then what is this? This is complete nonsense, because this is a contradiction. Because we know that D is undecidable, right? And we cannot have a Turing machine for that. Right, but it's not enough for you to have it as an illustration like this. You need to write it down, because this is a theory course. So you need to write everything down formally. So let's read through and see the formal way of writing everything down that we discussed verbally. So for the algorithm part of the recipe here, you need to say, okay, after we have our assumptions like this, we have this as a subroutine. So we have M in our hands as a tool. So you say, okay, we construct a new Turing machine MD that uses M as a subroutine. Yes. And MD first runs M on input W. Doesn't mean it could be input X, it could be input W, doesn't matter. And it negates the result, right? It negates the result like this in our illustration, but it's also enough to just say that it negates the result. And then you also say, okay, if M accepts, MD rejects. If M rejects, then MD accepts. So you also define clearly what the behavior looks like one more time. And at the end of the day, you say, therefore, MD decides D. And this is a contradiction. So you would think that this is enough, but no, it's not, because you need to still show the correctness of the Turing machine MD. Okay, you constructed some Turing machine, right? But how do we know that it decides the diagonal language? I mean, it's right in front of our eyes, right? But again, this is a formal theory course, so you need to prove every statement that you make, even though it's obvious, you need to still prove it. So as long as if we didn't prove it, then it's not correct. We don't know it, okay? Therefore, you need to show correctness. And correctness consists of two parts. First of all, you need to show soundness. So this means if you have an input that is in the diagonal language, then you need to show that MD that we just constructed accepts that input, right? And you also need to show completeness. This means if our input is not in the language D, then MD would reject the W. If you show this and that, then this means that your Turing machine correctly decides the diagonal language, right? So one more time, First property is soundness. Next property is what? It's completeness. Right. Okay, so how do we show it? We start from the left-hand side of the implication. So we say, okay, an input is in the diagonal language. So what do you know from this? Basically, you know that so let me rephrase the question. What does M do with this input? So in these proofs, you basically walk through your Turing machine one by one with the information that you know about the input, if it's in the language or not, and you see what happens with your input to prove the correctness. So if W is in the diagonal language, what does M do with it? Remember, M was the Turing machine for the complement. So basically, you know, M rejects W by the definition of the complement. So what was the complement? The complement is basically the exact opposite of the diagonal language. So if there's an input in the diagonal language, then it's not in the D complement. Then M would reject W because M decides the complement. So if M rejects W, then what happens afterwards? So we went into the M rejects W, then what happens? It gets negated, right? So we say, okay, then I would accept W, right? And then because of this, MD also accepts W. So the path for W that is in the diagonal language looks like the following. You go into the M would reject because it's in the D, then it won't be in the D complement, then it gets negated, then you accept. Okay. Now completeness. So what happens if W is not in the language D? Then it's basically the exact opposite. Let me write it down quickly. So M would accept W because it's not in the diagonal language. It will be in the D complement. So then I would reject W and MD rejects W. Let me show you the path one more time. So if W is not in the diagonal language D, right? This is our only assumption. Then it will be rejected by the Turing machine that decides the complement because the complement is the exact opposite. So, sorry, if it's not in the language D, then it's in the language D complement, so it accepts. Then it gets inverted by the Turing machine I. Then I would reject it, and it will be rejected by the Turing machine MD as a whole. Okay. So after you also have the correctness, let's walk through one more time what we did. We assume that the complement is decidable, right? From this we know that there's a Turing, this is our only assumption. From this we know that there exists a Turing machine that decides the complement. Using that Turing machine, we created another Turing machine that decides language D, diagonal language, that we know that is undecidable. So we constructed this Turing machine MD using this assumption, M. After we have the algorithm for this, we also show the correctness of that Turing machine MD. So MD actually decides diagonal language D, right? So after we have all that, this means that we arrive to a contradiction. And why? Because using our assumption, we basically showed that we could actually decide the diagonal language. And this is completely wrong. Why? Because diagonal language was undecidable in the first place. So assuming the complement is decidable, we show that we decide diagonal language D, which is completely wrong. Therefore, our assumption must be wrong because of this contradiction. And what was our assumption? Our assumption was that the complement is decidable. If it's wrong, what does hold? It holds that the complement is undecidable. So this proof that we did is sufficient to show this. And we're done.